This video is part 4 of Chapter 2, Neuroscience for PSY 110S, the Psychological Sciences. In this section, we will be talking about the brain and how it is structurally set up, what we know about functionality of those various components of the brain. The human brain has a long evolutionary history, like the brains of all creatures. It evolved from just having brainstem structures that link the brain to the spinal cord, eventually evolving all of the capacities that really make us human beings, primarily in terms of the cerebral cortex. You know, the things that house our personalities, our ability to use language, our ability to do planning and solve problems and make music and everything else. As you travel up the brainstem and out into the cortex, the type of information work, the kind of processing that's engaged in, gets to be more complex. So there's things I just described, things like intelligence, problem solving, personality, planning. Those sorts of things are very complex processes that require a lot of interconnectivity and a functioning memory system, etc., in order to accomplish them. The cortex enables all those complex things that I've just described, including the various cognitive processes of decision-making, language, and perception. So making sense of the environment around us. The structures below the cortex are those things that are essential for life. So you have the basics of breathing and regulating heart and digestion and all of that. Without a brainstem, you're not going to be doing that. Those functions won't occur. But there's also real basic survival-related cognition. Things like fight or flight, recognizing danger, processing basic emotional responses that are tied to survival. For example, being able to respond with violence toward a threat is a basic component of many species, humans included, or the basic emotional responses to the weak or the young are also more brainstem level kinds of experiences. We'll start our exploration of how the brain is built with that central core. So the brainstem, and sort of the old, what my physiological psychology professor called the old monkey brain, which is a woefully inaccurate way of describing it. What he meant by that was it is, evolutionarily speaking, older and more tied to really basic survival-related aspects of our functioning. So the brainstem is that portion of the brain that goes from the spinal cord up to the thalamus. As we continue the journey upward, the medulla is a portion of the brain that's associated with some survival-related physiological functions: heartbeat, breathing, blood pressure, digestion, and swallowing. Any sort of disease or injury that affects the medulla is going to have pretty immediate survival related issues because of its essential function in that space. The pons, which your author's note is Latin for bridge, it functions as a connecting point between the cerebellum, which is another part of this central core or older brain. So it connects the cerebellum to the rest of the brain. The pons has been most strongly connected to sleep, both the process of sleep and the experience of dreaming. The reticular formation is a portion of the central core that has bundles of neurons that run up the center of the brain stem, and then directly connecting up with the thalamus. It is heavily involved in our various states of arousal. So you're talking about wakefulness, sleep, and everything in between, and our perception of consciousness. So, when you have reticular formation, injury or damage or disease, that can impact strongly our ability to regulate our experiences of arousal. So you could have hyperarousal, where the arousal level is persistently too high, interfering with sleep. You can have underarousal as well, where the person is experiencing not enough activation. The cerebellum, sometimes, and this is back to my undergraduate physio instructor, he called it the little brain, which is more of just a reflection of the size of the cerebellum. It's comparatively smaller than the cortex, but it has a sort of cortex-like shape. It's involved heavily in coordinating how we move, integrating the sensory inputs that are related to balance. It's also connected to how we learn motor skills. I used an example previously of what if I lost my mind and decided to learn how to play golf. The cerebellum would be pretty heavily involved in learning the coordinated movements that are responsible for golf swings, for example. The thalamus is involved in a whole lot of different functions. The primary function of the thalamus is the integration and coordination of information from the sensory systems. So you've got all the various senses, visual, auditory, taste, touch, as well as information coming from the sensory neurons in the muscles. And basically the thalamus is a way station. It decides where to network out that information. So let's say that you are next to the stove and you don't realize that one of the burners is on, and you reach out your hand, and the sensory neurons in your hand recognize the extreme heat. That's going to send a message up, and it will go through the thalamus very rapidly, and then an instruction will come from the motor cortex to move your hand. There won't be a whole lot of thought about it until afterwards. It will, that information will come in through the thalamus, and it will be like, emergency, move your hand, real quickly. Other kinds of sensory information are more complex and require a lot of integration. So think about what it takes for you to read the words on the screen. You have to take visual information, coordinate it, sending it to various locations in the cortex that involve translating the visual stimuli that you see through the eye, through the visual cortex, and then you have to integrate that with your memory, knowing what the words are, what they mean, how they translate. The fact that I'm talking too, you have auditory information coming in through the auditory cortex, is going to go to the thalamus and then feed that out to the various portions of the rest of the brain that help you to sort through the words that I'm saying. Are any of the words familiar? If they're familiar, you're going to process them really fast. If they're not familiar, much slower. So you'll have to really think about them and then integrate them. So as I'm talking, you're doing a lot of that. The thalamus is doing a lot of directing of information to various parts of the cortex. Simultaneously, you're looking at the screen and taking in visual information. All of that has to be directed to the right parts of the cortex along the way. Finally, you've got the basal ganglia, and these are on the outside of the thalamus. They're concerned. They're connected mostly to starting physical movements. And, it's one of those things you forget about. It's like you're sitting in a chair and then you're going to get up. The brain has to have a way of saying, yep, we're going to do that. And we're going to do it right now. So it has that initiation purpose for creating physical movements. Damage to the basal ganglia will mean that there will be interference in that kind of activity within the brain. Now, your authors provide you with this visual so that you can kind of get a sense of where these structures are. Notice that they are in the center of the brain. So in the first image here, you have this center portion, this older portion of the brain. You go up the medulla, through the pons, through the reticular formation, and to the thalamus. Now the cerebellum sits right up above the spinal cord. Remember its important role in coordination of movement. As inside, hidden inside the cortex, you have the basal ganglia, the hippocampus, and the amygdala. The amygdala is really, and we'll talk about these more here in a second when we talk about the limbic system, the hippocampus is really heavily involved in memory, and the amygdala is heavily involved in emotional regulation, particularly of hot emotions like fear and anger as well. So we'll kind of pull some more of that information in the next few slides. The limbic system involves some of the structures that I described just on the last slide, and some of the elements that are connected to the endocrine system. So positioned on top of the brainstem is what's referred to as the limbic system. It includes the hippocampus, the hypothalamus, and the amygdala. The hypothalamus controls the pituitary gland and the autonomic nervous system and plays a role in regulating all those basic drives that we talked about earlier in this chapter. As I just mentioned, the hippocampus is heavily involved in the formation of new memories and the ability to generate new connections through a process that's called neurogenesis. So of creating new connections between ideas. So you experience something, it needs to be integrated with previous memories, and in a sense, what it's doing is creating a trace for that new experience in the form of a memory. And, the brain doesn't do anything without physical connections, so it's going to be literally building new connections with neuronal branching so that you can have this ongoing sense of continuous connected experience. The amygdala, as I just mentioned on the previous slide, has a lot to do with emotional regulation. So things like fear, anger, and aggression, which I described as quote-unquote hot emotions. These are the emotions that are the most directly connected to our biological survival. So if you're under threat, like think mountain lion on your porch, your amygdala is going to go, yep, that's a scary thing. Let's ramp up the hot emotions that will enable us to either fight or flee. When we're extremely fearful, that pressure you feel to run away, or when you're threatened, that experience of pressure to fight back, all of that is connected to the function of the amygdala. Really famous, perhaps infamous, set of studies many decades ago showed that electrical stimulation of the amygdala in cats, for example, when that stimulation is turned on, think of your favorite image of a very hostile cat with its hair standing on end, its back arched, hissing, and rather prepared for biting your face off. And then you turn off the stimulation, the cat goes back to being a pleasant little kitty. So, that's some of the early research that showed the importance of the amygdala. We know that in humans, if there is damage or disease that involves the amygdala, it can lead to changes in those emotional regulation abilities that people have. Now, the amygdala doesn't do this work on its own. It's connected to all kinds of other structures. It's, linked up with the memory system, with a variety of other systems, especially the hypothalamus and the thalamus, because, I started off this whole semester with the idea that the human experience is made up of thinking, feeling, and acting. You have to have your feeling components, the survival-related ones, connected to the thinking components, connected to everything else. So think about how, little tiny kids, toddlers, they have very little off switch. You have a toddler that's in full-on tantrum mode, really angry about something. They just blow up. They have very little control over their emotions. Until their cortex gets a little smarter, a little bigger, a little more developed, they're not going to be able to override the messages coming from the amygdala that say, hey, blowing up is the way to go here because my survival is being threatened. So as kids grow, ideally, the cortex starts to put some thinking on top of that, interpreting situations more appropriately, slowing down the emotional responding, and so on. So the cortex, and this is a stock image of a brain that has been quote unquote fixed, meaning it's been infused so that it has a more solid appearance for examination. The cerebral cortex is where all of those high level processing things happen. Some describe it as an information processing center, which is more or less accurate. It's the place where intelligence happens, where problem solving happens, where personality is housed, where the integration of our own personal story is housed. It's also where, as you can see on the image, you have this split right down the middle of the brain. Those two hemispheres of the brain, in some cases, they have duplicate function, but in others, they have function that's pretty segregated. So you have to have a way for the hemispheres to talk to one another and integrate their different perspectives. What does that integration is a structure called the corpus callosum, which is a dense network of fibers that link the two hemispheres together. The brain is divided into a set of lobes. There's the frontal lobe that's in the front part. So if you take your hand and you put it over your forehead, inside your skull, where your hand is, that's where the frontal lobe is located. Anatomically, it's in front of what's called the central fissure. There are lots of these little peaks and valleys along the ridges within the brain. So it's in front of the lateral fissure and above, or in front of the central fissure and above the lateral fissure. The parietal lobe is just behind that, behind the central fissure, but still above the lateral. The temporal lobe is below the lateral fissure, and the occipital lobe is on the back of your head, like if you took your hand and put it where those two big bumps, those bony bumps on the back of your head are. The occipital lobe is right inside there, lower back of each hemisphere. It's often easier to think about this looking at a visual. So if we find central fissure, that's this black line right here in between the primary motor area and the primary somatosensory area. So the frontal lobe is in front of the central fissure and above the lateral fissure. So that second black line there going horizontally is the lateral fissure. Below the lateral fissure is the temporal lobe. And you can see the arrow pointing to the darker, slightly darker orange primary auditory area. In the occipital lobe, which is green, the dark green is the primary visual processing area. The parietal lobe is right here. The primary somatosensory area is where you have integration of information from the body and the sensory organs, where you do some initial processing to make sense of them. And then you have a primary motor area where it's basically just laid out, mapped to your body. There's an area for hands and fingers. There's an area for arms. There's an area for your trunk. There's an area for your legs, area for your face, etc., etc. The basic rule is the more sensitive the area of the body, the more space, the more square footage you get in the brain for it. Taking a little closer look at the motor and somatosensory cortices, the motor cortex, which is directly in front of that central fissure in each hemisphere, allows for purposeful movement in the various parts of the body. The way the brain is set up, each hemisphere controls movements that are intentional, meaning you choose to do them, on the opposite side. So if you raise your right hand, shake your hand, wave at someone, that is coming from the left side of your brain in the motor cortex assigned to your right hand. If you move your left hand, that's coming from the right side of your brain. And as I just said, the amount of motor cortex space that's dedicated is dependent on the complexity of the type of movement that you need. So your hands, for example, get way more space in the cortex because we use them for such fine-grained work. They're heavily innervated. They require a lot of precise, organized, coordinated activity. So there's more acreage assigned to the hands than, say, to the skin covering your stomach, your belly. Not so important there. The somatosensory cortex is directly behind the central fissure, and this is where we integrate sensations that come from the body, and it does a certain degree of integration. So, primarily you're talking about sensory information coming in from the skin, so pressure, temperature, but also inside the body. There are lots of neurons that are responsible for determining, how are your arms and legs currently positioned. Really important for things like walking. Your knees, your hips, your ankles, your feet, even your back and your shoulders and the way your arms move. All of those have to be coordinated, and the somatosensory cortex is going to be pulling in all that information and making it so that you have the right data to help you make those coordinated activities. Again, you got a contralateral organization, meaning right side information is going to go to the left side of the brain. Left side information is going to go to the right side of the brain. Just like with the motor cortex, the amount of sensory motor cortex that is allotted to a given body part is going to be connected to the degree of sensitivity required of that body part. Now, your authors provide you with this bizarre-looking set of drawings called a homunculi. When you lay out the motor cortex and the somatosensory cortex, what you see is that we have a lot of space allotted to the tongue, the lips, the face, and the hands, especially the thumb, and much less to the trunk, the neck, the hip, the knee, more to your feet, and so on. So output, motor cortex is going out to the body to control actions that the body needs to take. The somatosensory cortex is similar in that you have a lot of input from the tongue, the face, the fingers, the thumb especially, much less for the rest of the body. Feet are big, but you're going to pull in information from that somatic sensory cortex that will integrate, this motor and the somatosensory cortices are going to be integrated with one another as well. So that you have, thing about walking. Walking is a really complex activity. So as kids learn to walk, they're in a kind of almost literal sense, wiring the connections between the somatosensory cortex and the motor cortex, and vice versa, to get the right inputs and the right outputs for people to do the things that they want to do. The visual cortex, as you remember from the drawing presented earlier, is located in the occipital lobe at the back of each hemisphere. It is responsible for making some initial sort of interpretations of visual stimuli. And we'll talk more about that in the next section of the lecture. The auditory cortex that I pointed out on the drawing earlier, it's located in the temporal lobes, sort of adjacent to where your ears are. It contains primary areas for auditory processing, so you're making sense of auditory information. If someone sustains damage to those primary auditory cortices, the person can become functionally deaf. So, I mean, their ear and the structures inside the ear may be fine. They may be perfectly functional. But if that auditory cortex isn't working, then the functional outcome will be the inability to hear, because you have to process the information in order to recognize that it exists. Same goes for the visual cortex. If you have damage to the occipital lobes, it wouldn't matter that your eyes are actually fully functional, or that your auditory or your occipital optic nerve, is fully functional. Without the cortex, you can't make sense of those signals, so you would be functionally blind. And that concludes this part of Chapter 2.